All right, everybody, in honors pre-calculus, everything that we've been doing in Unit 2 so far has been building to this. This is lesson 2.5, zeros of polynomial functions. So today we're going to start learning how to solve for the real and imaginary zeros of polynomial functions. You already know exactly what a zero is, I hope, at this point, because we've looked at x-intercepts as zeros throughout Unit 1 and Unit 2. We also, at this point, know what a polynomial is. It's any function that's made up of different types of x terms with different exponents. For example, this one right here is a polynomial. And we've also now learned about complex numbers, right? The imaginary numbers. So now we can find all of the real and imaginary zeros of polynomial. And so our essential question today is, how do you find the zeros of a polynomial function? As simple as that. All right, I'm going to switch over to the notes. Here are our notes. Again, we're looking at lesson 2.5, zeros of polynomial functions. So the first thing that we're going to talk about here is the fundamental theorem of algebra, which says that if f of x is a polynomial of degree n, where n is greater than 0, remember a degree is the highest exponent on an x, then f has at least one zero, real and or imaginary, in the complex number system. So a complex number can be real, imaginary, or a combination of the two. So every polynomial has at least one zero. All right. Now you might think about, hey, we've seen quadratics that don't go through the x-axis. So don't those not have zeros? And the answer is that's why we need to think about the imaginary zeros. So if a polynomial doesn't have real zeros, then it definitely has imaginary zeros. But we're going to talk even more specifically about rational zeros today. So in case you forget what a rational number is, we can always represent it as p over q, where p and q are both integers and q is not equal to 0. Remember, an integer is a positive or negative whole number, a number that you would commonly write on a number line. And so any rational number can be represented by p over q, where p and q are both integers. This can be written as a fraction of integers or as a decimal that is either repeating or terminating. Terminating meaning that it stops. Rational zero test. The possible rational zeros of a polynomial can be represented by plus or minus p over q, etc. All right, so we're going to actually come back to the rest of these definitions after we take a look at example 1. So let's take a look down here. Determine the number of zeros, all types of each polynomial function. So what we need to think about is, first of all, take a look at the degree, and that always tells you the total. So in letter A, we know right off the bat, this is x to the first, and that's the highest exponent. So there should be one total. In letter B, we have an x squared, so there should be two total. In letter C, we have an x cubed, so there should be three total. In letter D, there's four total. So our job now is to figure out how many of these are real and how many of them are imaginary. So now we have the total. I want us to break this down further. In the first one, this is a line. It crosses the y-axis at a y-intercept of -2, and it has a slope of 1. That's definitely going to have a real x-intercept. It's going to be visible on the graph. So that means that this has one real zero, which means that that's all of them, right? Because there's only one total. So there's going to be 0 imaginary zeros. In letter B, we have x squared minus 6x plus 9. And so what I'm going to do here is, there's a couple different ways we could approach this. We could try looking at the graph and see if we can see the x-intercepts. That would make them real. But we can also factor this, and this factors to x minus 3 and x minus 3. And so we have a 0 of x equals 3 and another one of x equals 3. So remember, this has a multiplicity of 2, right? The 0 of 3 has a multiplicity of 2 because it showed up twice. And those are real numbers. So even though it repeats, it still counts as 2. So that's 2 real zeros. And again, that's all of them. So now we have 0 imaginary zeros. Okay, but let's keep going. Letter C, 3 total. I can factor out an x, and we're left with x squared plus 4. Well, the x can represent the 0, x equals 0. X squared plus 4 is a little trickier. If we want to try to break it down, we have x squared plus 4 equals 0. X squared equals -4. So x equals plus or minus the square root of -4. And without going too much further, we can tell, right, that this is the square root of a negative number. So that's going to be imaginary. And we have the positive and negative version of that. So that means we have 1 real 0, which is literally the number 0. And this is 2 imaginary zeros. So if we looked at this graph, we would go through the x-axis at x equals 0, and that's the only time. This would not be represented visually on the graph, but these are imaginary zeros that are still making this an x cubed. Let's take a look at letter D. We have 4 total. This is actually a difference of squares, so we can break it down into x squared plus 1 and x squared minus 1, right? If we FOIL this, the outer and the inner will cancel. We'll get x to the 4th minus x squared plus x squared minus 1. And x squared minus 1 is another difference of squares. So we have x squared plus 1, x plus 1, x minus 1. So this factors, or I guess, gives us a 0 of -1. This factor gives us a 0 of 1. And over here, much like in letter C, this is going to give us plus or minus the square root of -1, or plus or minus I. But the question is not actually asking us for the zeros. It's just a number of zeros. So we have a -1 and a 1, so that's giving us 2 real zeros. And then this is representing 2 imaginary zeros. All right, so that's example 1. I want to take a look up at this complex 0 situation. Back at the top, if a plus bi is a 0 of a polynomial function, then a minus bi is also a 0. What this means is that imaginary or complex zeros always come in pairs, and you can see that in C and D that we just looked at here, right? We had plus or minus the square root of -4 and plus or minus the square root of -1. Those are both considered pairs of imaginary zeros because we have the positive and the negative version. It so happens that for both of those, if we kind of wrote it in this form, there wouldn't be an A would have been 0. It's just the imaginary part, but you can see there's the positive and the negative version for both of these, for this and for this. So what that means is that the number of imaginary zeros is always going to be even because it always comes in pairs. Let's take a look at example 2. This time, we're going to find the rational zeros using the rational zero test. So think about that. There are real and non-real, or real and imaginary zeros. Within the real number realm, there's rational numbers, right? Rational numbers are the p's over q's. There might be other zeros that aren't rational. So in example 2, we're going to be breaking down the zeros a little bit further, and this time we're not necessarily going to be listing all of them. We're only looking for the rational ones. And so to start, we're going to use what's called the rational zero test, which I started to read earlier. The possible rational zeros of a polynomial can be represented by plus or minus p over q, where p is a factor of the constant term and q is a factor of the leading coefficient. So we want p's to be factors of the constant and q's to be factors of the leading coefficient. Note that p and q can potentially be many different values for the same polynomial. Let's take a look at what that means. So in letter A of example 2, we've got the constant here is 1, and our leading coefficient is also 1. hiding right there. So the p's are, as it said at the top, the factors of the constants. Okay, so the only factor of 1 is 1. And the q's are the factors of the leading coefficients. The only factor of 1 is 1 again. So possible rational zeros, I usually write it as PRZ. So the possible or potential rational zeros are any p over any q, and then it can be plus or minus. So this is really only plus or minus 1 over 1. That's the only option. So if there are rational zeros, it's 1 or negative 1. That's it, okay? And to check this, what we can do is plug each one of these in and see if we get 0. So if we plug in 1, we get 1 plus 1 plus 1. That's definitely not 0. If we plug in negative 1, we're going to get negative 1 minus 1 plus 1 is negative 1. Okay, so neither of them gave us 0. So that means that this letter A actually has no rational zeros. We can say for a fact that there are no other ones because there aren't any potentials. That's what this test tells us. So we know from example 1 that there are 3 zeros here, but none of them are rational. So they must be either irrational, real zeros, or imaginary. And we can actually look at the graph to see if we can see any of them. So let's take a look since we're here. Looking at x cubed plus x plus 1. Okay, so there's definitely one real zero, but it's definitely not rational, so it must be irrational. And the rational zero test doesn't help us find that, and the question doesn't ask for that. So we are not going to find even an approximation for that 0, but you can tell it's not 1 or negative 1. It's between 0 and negative 1. Let's keep going to letter B. This time, we're looking for potential P's and Q's. P's are the factors of the constant term, which is now -6. We don't have to pay attention to the sign. We don't care about if it's positive or negative, because remember, when we write the PRZs, the possible rational zeros, we're going to write plus or minus every time. So all we need to do is write down all the factors of 6. And I know that 1 times 6 is 6, and 2 times 3 is 6. So I have 1, 2, 3, and 6 as potential P's. For the Q's, we're looking for, again, the factors of the leading coefficient, which is 1. So it's just going to be 1. So now if we write out our possible rational zeros, we have to pair up every P with every Q. Now there's only one Q, it's a 1. So we're going to put plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, and plus or minus 6 over 1. And that's really just 1, 2, 3, and 6, right? So we didn't really need to write the over ones, but I wanted you to see that. If there was another potential Q, like maybe this was also has a 2, we'd have to go back and pair up every P with the 2 also. But this is all of them. So that's all of our possible rational zeros. And now we have to check each one to see if it is true for this equation. So what I'm going to do here is, instead of plugging in every single one, actually, you know what? That's not a bad idea. I'm going to first start by just kind of graphing this. Talking to myself. Minus 3x minus 6. What do we got here? All right, if I had to guess, I would say we have one at -1 and at 2. Let's check the table just to be sure. -1 has a y of 0, 2 has a y of 0. Okay, so it worked. I know based off of these possible rational zeros that none of them were bigger than 10 or smaller than -10. So I don't have to zoom out on the graph or anything. That was enough. So we have -1 and 2. Again, this is an x to the fourth. It's a degree of 4 polynomial. So there are two other zeros somewhere, but they're not rational. These are the only rational ones. Let's check letter C. So this time we can have up to 3. Our p's are our factors of the constant term, which would be 1 and 3. Our q's are the factors of the leading coefficient, which would be 1 and 2. So our possible rational zeros are going to be every p paired with every q. So we have plus or minus 1 over 1, plus or minus 3 over 1, plus or minus 1 over 2, and plus or minus 3 over 2. So we're going to take a look at this, and let's take a look at the graph. I'm going to plug in this function. Graph it. And again, we don't have any possible rational zeros that are below -10 or above 10. So if there are x-intercepts that are rational, they're going to show up on this window. It looks like we have one at -3. That's one of our potentials. If we look at the table, -3 does have a 0. So -3 is one of them. And 1 is another one, and that was on our list, so that's good. And there was one more on the graph between 0 and 1. Okay, so let's see. We have a couple options here. We could go to second trace, go to 0, which is number 2. Go a little bit to the left and a little bit to the right and see if we can get it. Oh, we got it. It's 0.5. Yep, that was on our list. So x equals 1/2 is the third one. And look at that. All 3 zeros this time were rational. There they are. Another option would be if we go to second window, change the independent variable to ask for the table, and then go to the table. We could have typed in 1/2 to see if the y value was 0, and it is. This is one way that you can actually go through this. Maybe you're a more methodical person and less of a visual person. You can test every single one. 1, -1. 3, -3. 1/2, -1/2. 3/2, -3/2. And any of them that have a 0 are the answers. Okay, so that's one other way that you could do this, just to make sure that you're checking every single one. Okay, so that is how you do the rational zero test. Please keep in mind that sometimes there are a gazillion different possibilities, because if you have a lot of p's and a lot of q's, you have to pair them all up. And speaking of that, let's take a look at example 3. We are going to find all the possible rational zeros of the following polynomial using the rational zero test. Then find all of the real solutions. All right, this question is a beast, but let's try it. So first thing we're going to do is exactly what we were doing in example 2. We're going to find all the possible rational zeros using the rational zero test. So in this question, our polynomial is set equal to 0, but we can clearly see that we have a leading coefficient and a constant that have a couple factors. So if the first thing I'm going to do is list out my possible p's and q's. The p's, remember, are the factors of the constant term. We don't care about the negative. And it is 12. So let's think. We have 1 and 12. We have 2 and 6. We have 3 and 4. And that's it. So I'm going to write them in order. The q's have to be the factors of 10. Again, we don't care about the negative. So it'll be 1 and 10 and 2 and 5. So now what I'm going to do is write out all of our possible rational zeros. And I have to pair up every single one of these p's with every single one of these q's. So this is going to take a little bit of work. I'm going to start by putting every p over 1. So we're going to have plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. Okay, then I'm going to go through and put every single one over 2. And as I'm going, if I notice that the fraction I'm about to write was already represented earlier, I don't have to write it. I'll show you what I mean. So 1 over 2, that's a new one. 2 over 2 equals 1. So I already have that, so I don't have to write 2 over 2. 3 over 2 is a new one. 4 over 2 equals 2, I already have it. 6 over 2 is 3, I already have it. 12 over 2 is 6, I already have it. Okay, now I'm going to put every p over 5. Plus or minus 1/5, plus or minus 2/5, plus or minus 3/5, plus or minus 4/5, plus or minus 6/5, plus or minus 12/5. Okay, none of those repeated. And now I put every p over 10, plus or minus 1/10. 2/10 is 1/5. I already have that. 3/10 is new. 4/10 is 2/5. I already have that. 6/10 is 3/5. I already have that. And 12/10 would be 6/5. I already have that. Okay, so that's all of them. Yep, I'm just checking my answer key. I did write all of them. So that is step 1. We found all of the possible rational zeros, and it was a lot. So this polynomial has at most 3 zeros. We don't know how many yet are rational, but it's definitely not this many. It's up to 3. So now what we have to do is figure out which of these are actually on the graph, because we are then told to find all of the real solutions. So first we're finding the rational solutions, and we're going to use those to find the real solutions as well. Find all of them. So and then we're going to have 3 solutions, just not sure what they are yet. Okay, so I am going to plug this into the calculator here and take a look at the graph. Negative 10x cubed plus 15x squared plus 16x minus 12. And my biggest possible rational zero is 12, and the smallest is negative 12. So my viewing window only goes from negative 10 to 10. It's possible that some of the zeros might be beyond, but so I would want to change my viewing window, except that I know I have at most 3 zeros, and I already see 3. So that's a good sign. It means we don't have any imaginary. But let's see if we can figure out what these are. So I have one that looks like it's right around negative 1, and one that looks like it's at 2. So first I'm going to check that. Do we have one at negative 1 and at 2? No. Okay, we do have one at 2. So the possible rational zeros are leading us to this. We have one at 2. Let's try to zoom in here. Maybe if we zoom in, we'll be able to tell better. Oh, okay, so I don't know if it's showing up well on camera, but it's this blue curve is a little bit to the left of the mark, so it's not quite at the negative 1. Let's see if we can figure out if it's on our list. Okay, I'm going a little bit to the left and a little bit to the right of it. Negative 1.06. Yeah, the tiniest slice or fraction that I have is a 1/10. So that's definitely not, that's smaller than a 1/10, lower than negative 1. So that's not on our list. Let's check the other one that we don't have yet, which is this one over here between 0 and 1. 0.5639. Yeah, that's not on our list either. So those must be irrational. They're not rational, because if they were rational, they would show up on our list right here. So let's see. We are going to try to find all of the real solutions. That means we need something to represent both of these. And we could just round those decimals, but we want to actually solve this for the exact solutions. And we can get exact solutions here. We don't need to rely just on a rounded decimal. So this whole list of possible rational zeros just gave us x equals 2. And what we're going to do moving forward here is we're going to factor that out of the polynomial to see what's left over. So here's what we're going to do. We're going to use synthetic division. So remember, x minus 2 represents a factor of x minus 2, right? Because if I set x minus 2 equal to 0 and solve for x, I would get x equals 2. So what that means is that we should be able to use synthetic division with this original polynomial to pull out the x minus 2 factor. So we put a positive 2 in front. We gotta write down our coefficients. Don't need any 0 placeholders for this one. And let's do it. So we're gonna pull down a negative 10. Negative 10 times 2 is negative 20. We get negative 5, negative 10, 6, 12, 0. Okay, so that's good news. We got a remainder of 0. So it really was a factor. We've got a constant term, an x term, and an x squared term. So this now factored to x minus 2 times this, negative 10x squared minus 5x plus 6. Okay. So let's see if we can get this to factor. I don't like when a is negative, so I'm going to actually rewrite this over here with a pulled out negative. So it's going to be negative x minus 2 positive 10x squared plus 5x minus 6 equals 0. Okay, so let's try to factor. So 10 might be 2 and 5 or 1 and 10. And you can try that as hard as you want, but it's not going to work. It doesn't factor. So when we are forced to try to find the zeros and we have a quadratic that doesn't factor, our next best option is the quadratic formula. So that's where we're going to go. We got everything in one question here. So we have a is 10, b is 5, and c is negative 6. And we're going to plug it into negative b plus or minus the square root of b squared minus 4ac all over 2a, which will be negative 5 plus or minus the square root of 5 squared minus 4 times a times c. 4 times a is 4 times 10 is 40 times 6, so it's going to be plus 240 all over 2 times a, so all over 20. So that's going to become, to the 20 can distribute here, so this becomes negative 1/4 plus or minus the square root of 265 all over 20. And let's think, 265. So I'm going to try to simplify that. I know that 5 can go into that, and 53. Yeah, we're stuck. 53 is prime. So that doesn't simplify. That's the simplified version. And now we found that our 3 zeros were x equals 2 and x equals negative 1/4 plus or minus the square root of 265 all over 20. That represents 2 different zeros, right? Because we have the plus and the minus version. If we go back to our graph, Let's see, what were the zeros? Let's just try the positive one. We had one at 0.563941. I'm going to write that up at the top. And if I type in this with the positive version, it should give me the same decimal approximation. 0.563941. Yep, see that? So this is the exact way of writing that approximated decimal. We like exact, all right? So that's what we wanted. That was a beast of a question, but we got through it. We had to do the rational zero test. Then we had to figure out which rational zero was actually on the graph. Then we had to use synthetic division to factor out the x minus 2. The quadratic that was left over couldn't factor, so we had to use the quadratic formula to find the exact representation of the other two zeros. Let's take a look at letter B. Find a fourth degree polynomial function with real coefficients that has a -1, -1, and 3i as zeros. Find a fourth degree polynomial. So this is kind of working a little bit backwards. We're given the answers. First, I want to make sure that you remember that if 3i is a 0, it means that we also have the negative version of that as a 0, right? That's something that we looked at on the front. We said for complex zeros, if a plus bi is a 0, then a minus bi is also a 0. And every question that we've looked at so far that had imaginary zeros had those pairs. So we really know 1, 2, 3, 4 zeros, and this is fourth degree. So we know all of them. So our function is going to have factors that give us these zeros. So if we need a -1 as a 0, the factor is going to be x plus 1, right? And there's another -1, so there's going to be another x plus 1. And then we have 3i and -3i, and that's going to work very much the same way. We're going to have x plus 3i and x minus 3i. We don't like the idea that there are i's in these factors, but we're going to be able to figure it out. So this would give us the -3i, this would give us the positive 3i. So when we multiply this together, we want to multiply the part with the i's first, because if we multiply or FOIL the x plus 1 with the x plus 3i, the I is going to get all mixed up, and by the end it'll cancel out, but it will have been a nightmare on the way. So whenever you have the imaginary portions of factors present, you want to multiply those together first. So we're going to have x plus 1 and x plus 1. Those can stay there. Let's see what happens over here. We have x squared minus 3i plus 3i. Okay, hold on. I forgot to say the x. It's minus 3ix plus 3ix. So the outer and the inner cancel out. That's because these are conjugate pairs, right? And then the last term would be plus 3i times minus 3i. So it's going to be -9i squared. And we could make that look a little bit nicer because I squared is -1. So that's really x squared plus 9. And to finish this up, we're just going to keep multiplying the factors together. So let's multiply the x plus 1 and the x plus 1. We're going to get x squared plus x is plus 2x. And then 1 times 1 is plus 1. And our second factor present is going to still be the x squared plus 9. And now we're going to kind of multiply these all together. So we're going to have to distribute. So we get x to the 4th. Good sign, because we're looking for a 4th degree. Plus 9x squared. Plus 2x cubed. Plus 18x. Plus x squared plus 9. Okay, so I distributed the x squared, I distributed this 2x, and then I distributed the 1. And now we're going to combine like terms for our final answer. There's x to the 4th. We have 1 x cubed term, it's plus 2x cubed. We've got a plus 9x squared, and an x squared is going to give us 10x squared, and then plus 18x plus 9. So that's our standard form with our decreasing exponents. And that's going to have all the zeros we wanted. If we graphed this polynomial, you would see that it had a 0 or x-intercept at -1. You would not see the 3i and the -3i because those are imaginary. They won't show up on the graph, but they do exist. Example 4, factors of polynomials. Find all the real zeros of this function, given that 1 plus 3i is a 0. All right. So here's the deal. Now we have a full complex number, 1 plus 3i, with a real and an imaginary portion. We're going to write the factors just like we did in the previous question. But think about this. If the factor was, or if the 0 was -1, the factor was x plus 1. If the 0 was 3i, the factor was x minus 3i. If the 0 is 1 plus 3i, the factor is going to be x minus 1 plus 3i, which you could rewrite as x minus 1 minus 3i. All right, we're going to do the same thing. We know that if 1 plus 3i is a 0, 1 minus 3i is also a 0. So it's x minus 1 minus 3i, which is going to be x minus 1 plus 3i. So we are going to try to do this without looking at the graph. And I don't know how to factor these parentheses out of that polynomial, right? The only ways we know how to factor are if it's quadratic, we can factor using our factoring methods. If it's bigger, we use long division or synthetic division. And we never learned how to do that with an imaginary number. So the first thing that we're going to do is combine these into one. So if we combine or multiply together the imaginary factors, hopefully the imaginary part will cancel out. So we're going to do x minus 1 minus 3i times x minus 1 plus 3i. So we'll get x squared minus x plus 3ix. So that's the x distributed to all three. Now I'll do the -1. So it'll be minus x plus 1 minus 3i. And then we'll do the -3i. So it'll be -3ix plus 3i minus 9i squared. So if we combine all of this, what's going to happen? The plus 3ix and the minus 3ix cancel. The plus 3i and the minus 3i cancel. We have x squared minus 2x plus 1 minus 9i squared, which really means plus 9, right? Because the I squared is -1 times -9 would be plus 9. And so this gives us x squared minus 2x plus 10. Okay, so what all of this means is that this x squared minus 2x plus 10 must be a factor of this original polynomial. And we can figure out if that's true by dividing it out. And we could use synthetic division or long division. Unfortunately, since this is a quadratic and has an x squared, we can't use synthetic division. So we're going to have to use polynomial long division to get this out of here. So let's try this. We have x to the 4th minus 3x cubed plus 6x squared plus 2x minus 60. And we're going to divide out x squared minus 2x plus 10. So this is going to be good practice. So let's remember, what do I have to multiply by x squared to get x to the 4th? And the answer would be x squared. I distribute the x squared to all three of these terms and write it under here. So it becomes x to the 4th minus 2x cubed plus 10x squared. I subtract this. I'm going to distribute the negative. The x to the 4th goes away. 2 minus 3 is -1x cubed. 6 minus 10 is going to be -4x squared. Bring down the next term, plus 2x, and then start again. x squared times what is negative x cubed? It's going to be negative x. Negative x times x squared is negative x cubed. Negative x times negative 2x is going to be positive 2x squared. Negative x times 10 is going to be negative 10x. We subtract this. Distribute the negative. X cubeds are gone. Negative 4 minus 2 is negative 6x squared. 2 plus 10 is plus 12x. Bring down the next term. And start again. X squared times what is negative 6x squared? It would be negative 6. Distribute the negative 6 to everything in front, and we get negative 6x squared plus 12x minus 60. That's great news. It's the exact replica of what's above it, which means that it's all going to cancel out when I distribute the negative. And we have a remainder of 0. That means that this indeed was a factor, which is what we wanted. So what we have left over is x squared minus x minus 6. So what we could do now is say that our original function could be rewritten as this original factor times the new factor, x squared minus x minus 6. And that's because we divided out x squared minus 2x plus 10. So we could rewrite it as being multiplied by the result, the quotient, to get the original, right? It's because multiplication and division are opposites. And what we're trying to do is find all the real zeros, okay? So hopefully this x squared minus x minus 6 has some real zeros in it. And lucky for us, that can factor. We have x squared minus 2x plus 10. And that becomes x minus 3 and x plus 2. Which means that our two real zeros are x equals 3 and x equals negative 2. So after all of that, the answers are 3 and negative 2. All right, and that's how you can do that without a calculator. Okay, so remember, those are the real zeros. The imaginary zeros or complex zeros were 1 plus 3i and 1 minus 3i. That gives us a total of 4 zeros, which makes sense because this has a degree of 4. All right, last question, letter B. Write the polynomial f of x as the product of linear factors and list all of the zeros. All right, this time we are going to use the graph. We're practicing lots of different strategies here. So we've seen how to do this using possible rational zeros. Now we're going to use the graph, and we're going to find every zero, even if some of them are imaginary, we're going to find them. Not necessarily on the graph, but we'll find them another way if we can't find them on the graph. So first, let me plug this in. We have x to the 5th plus x cubed plus 2x squared minus 12x plus 8. And from the graph, it looks like negative 2 and 1. Can I confirm that on the table? Let me reset my table here to auto. Negative 2 and 1, yes. So from the graph, we found x equals negative 2 and x equals 1, positive 1. All right, so what we're going to do to start this off is we're going to use synthetic division to divide these zeros out. So let's try this. If we set up our L, we can put negative 2 in front. Remember, negative 2, a zero of negative 2 represents a factor of x plus 2. So we'll still write the negative 2 in front. Don't forget we need a placeholder 0 for the x to the 4th. So it's going to be 1, 0, 1, 2, negative 12, and 8. And let's see what happens. We'll pull down a 1. 1 times negative 2 is negative 2. Add to get negative 2. Negative 2 times negative 2 is positive 4. Add down to get 5. 5 times negative 2 is negative 10. Add down to get negative 8. Negative 2 times negative 8 is 16. 16 minus 12 is 4. 4 times negative 2 is negative 8. Good news, we got a remainder of 0. So if our original function was as written, x to the 5th plus x cubed plus 2x squared minus 12x plus 8. Now we're saying that if we pull out x plus 2, what's left over is, and this is a constant, x term, x squared, x cubed, x to the 4th. We have x to the 4th minus 2x cubed plus 5x squared minus 8x plus 4. We can go one step further though, because we know that there's also a 1. So I'm going to kind of layer the synthetic division like we've done before. Remember, we don't include the remainder in the new one. So we'll bring down the 1 and do this all over again. Okay, we got another remainder of 0, which is good news. So now the factored form is getting better, right? We're trying to get all linear factors. So far we have one linear factor. We're about to have a second one because we have x plus 2 that we pulled out before. And now we're breaking down this factor using the 1, right? This represented this factor. Now we're pulling out the 1, and now we're left with this. So the 1, a 0 of 1 represents a factor of x minus 1. And what's left over now should be 1x cubed minus 1x squared plus 4x minus 4. All right, so we've got two linear factors. One that is still degree of 3. We want all linear factors, so we've got to keep going. I already used up what was on the graph. So real quick here, I'm going to graph the factor that we're still trying to break down to see if we can see anything else left in there. I'll show you what I mean. On the graph, what you'll be able to see as soon as it loads is that we still have a 0 or a x-intercept at 1. And then what that means is that the original had 2 x equals 1s. It had a multiplicity of 2 for the x equal 1. And that wasn't necessarily clear based off of the graph. It might have bounced off the axis, which is usually a good sign that it shows a multiplicity of 2. But now we know for sure there's another 1 hiding in there. So we're going to go another step further with this synthetic division. Remember, again, we don't include the remainder. We're going to pull out 1 again. So let's do that. And we get another factor of x minus 1. And what's left over this time is x squared plus 4. Okay. So the question said to list all the zeros. The zeros that we have so far are -2, 1, and 1. We still don't have only linear factors, right? This is still a quadratic. And we don't have all of the zeros. We have 3 zeros. We're supposed to have 5. So x squared plus 4, if we take a look at that graph, I typed it in already, you'll see it does not go through the x-axis. So we don't have any more real zeros. The rest must be imaginary. So if we set that last factor equal to 0 and solve it, you'll see that we get plus or minus the square root of -4, also known as plus or minus. Remember that the negative in here can become I, and the square root of 4 is 2, so this is 2I. So our last two zeros are 2I and -2I. Then we come back over here, and if we really wanted to write this as linear factors, think about all the way back up here. We had linear factors that had I in them in this question, and technically in this question as well. So this is what we're looking for in our final answer. And if we know that zeros are 2I and -2I, we can break this down one step further. X plus 2, x minus 1 stay the same. X squared plus 4 we can write as x plus 2I, x minus 2I. So that's the final factored form with linear factors. This part is kind of weird. You can't just, in your head, break this into this. You have to find what the zeros are and then write each zero subtracted or added from x like this. All right, so that is the last question. That brings us to the worksheet. And I looked over the worksheet before I started recording. I didn't find anything popping out as anything I wanted to remind you of. Just make sure that you read the directions and remember the answers are available for you to check your work as you go. Let me know if you have any questions. Thank you so much for watching, like always.